Assalamualaikum, Madam. My name is Muhammad Haziq Muizuddin. I'm from class DAM 2C. My partner is Abu Darda bin Abu Zaganesh. Today we'll present to you about series DC motor. What is series DC motor? In a series DC motor, the field is connected in series with the armature. The field is wound with a few turns of large wire because it must carry full armature current. This type of motor develops a very large amount of turning force, called torque, from a standstill. Because of this characteristic, the series DC motor can be used to operate small electric appliances, portable electric tools, cranes, winches, hoists, and the like. Another characteristic is that the speed varies widely between no load and full load. Series motor cannot be used where a relatively constant speed is required under conditions of varying load. A major disadvantage of this series motor is related to the speed. The speed of a series motor with no load connected to it increases to the point where the motor may become damaged. Usually, either the bearings are damaged or the winding fly out of the slot in the armature. There is a danger to both equipment and personnel. Some load must always be connected to a series motor before you turn it on. This precaution is primarily for large motors. Small motors, such as those used in electric hand drills, have enough internal friction to load themselves. A final advantage of series motor is that they can be operated by using either an or DC power source.
So those is the video of how DC motor work.
You can find DC motors in many portable home appliances, automobiles, and types of industrial equipment. In this video, we will logically understand the operation and construction of a commercial DC motor. Let's first start with the simplest DC motor possible. It looks like this. The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards. This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor.
So they will have to...
Here is the trick to overcoming this problem. Add one more loop to the rotor, with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source. So a motive force is always present in the system.
Yeah. We add some more coil.
Moreover, the more such loops, the smoother will be the motor rotation.
Oh, I see.
In a practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will enhance magnetic flux interaction. Spring-loaded commutator brushes help to maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of the electromagnet is powered from the same DC source.
They will
The
act
field
as
coils can be
electromagnet.
connected to the rotor windings in two different ways: parallel or series. The result is two different kinds of DC motor constructions: a shunt and a series motor. The series wound motor has good starting torque, but its speed drops drastically with the load. The shunt motor has a low starting torque, but it is able to run almost at a constant speed, irrespective of the load acting on the motor. Unlike the other electrical machines, DC motors exhibit a unique characteristic: the production of back EMF.
Back electromotive force.
A rotating loop in magnetic field will produce an EMF according to the principle of electromagnetic induction. The case of rotating armature loops is also the same. An internal EMF will be induced that opposes the applied input voltage. The back EMF reduces armature current by a large amount. Back EMF is proportional to the speed of the rotor. At the starting of the motor, back EMF is too low, thus the armature current becomes too high, leading to the burnout of the rotor. Thus, a proper starting mechanism that controls the applied input voltage is necessary in large DC motors. One of the interesting variations of the DC motor is a universal motor, which is capable to run under both AC and DC power sources. To know more about it, please check the next video. Thank you. You can find DC motors in
Okay, so this is the example of motor calculation. There were several types of motor calculation. First, we have calculating mechanical power requirement. Second is torque speed curve, a numerical calculation, then sample calculation, and finally thermal calculation. So there's several examples. For first is the calculating mechanical power requirement. Physically, power is defined as the rate of doing work. For linear motion, power is the product of force multiplied by the distance per unit time. In the case of rotational motion, the analogous calculation for power is the product of torque multiplied by the rotational distance per unit time. So they have over there P ROT, so rotational mechanical power, is equal to torque multiplied by angular velocity. And the second example given is numerical calculation. For an ironless core DC motor of relatively small size, the relationship that governs the behavior of the motors is various circumstances can be derived from physical laws and characteristics of the motors themselves. Kirchhoff's voltage rule states the sum of the potential increase in a circuit loop must equal the sum of the potential decreases, says the Kirchhoff voltage law. When applied to a DC motor, when applied to a DC motor connected in series with a DC power source, Kirchhoff voltage rule can be expressed as the nominal supply voltage from the power source must be equal in magnitude to the sum of the voltage drop across the resistance of the armature winding and the back EMF generated by the motor. So, and they have the equation of V base O, or power supply volts, is equal to current multiplied by terminal resistance ohms plus V back EMF volts. The back EMF generated by the motor is directly proportional to the angular velocity of the motors. The proportionality constant is the back EMF constant of the motor, VE W multiple KE, where W is angular velocity of the motors, K is back EMF constant of the motors. Thank you. So that's all is about our presentation today about DC motors. We appreciate your attention and thank you.